two or more parties. It specifies obligations, permissions, and prohibitions. So for the parties to engage in certain fashion with each other, do certain things. And the main properties a contract usually has is it has identifiable parties. So that's required by law for sufficiently big contracts, you could say. I mean, of like at least 10,000 euros. And also to make sure that you know who to sue if you want to go to court. They usually supposed to exhibit consideration, which means that there are multiple actions involved, and these should be such that each party has a fair exchange in the sense of giving something and receiving something in return. And by default, they're usually confidential in the sense that only the participating parties know the contents and the state of a contract, unless there's regulation that requires disclosing that information to others. Examples would be sales contracts, service contracts, rendering services, leases, all kinds of financial contracts, loans, bonds, derivatives, structured products, insurance contracts, shareholder agreements, transportation contracts of people, like mobility, or of goods in the sense of transportation of, as I mentioned, goods. What would be a good semantic model of contracts then? A basic observation about a contract is that given a sequence of events, so the actions by parties usually, is it acceptable? Is an acceptable and complete execution of the given contract or not? So the fundamental idea then is to let a contract denote the set of acceptable complete executions, which means that all the other ones are not acceptable or complete. In particular, two specifications that denote the same set then are considered equivalents. So we'll get to the specification part in a second. What are these events? Most important events are transfers of resources. So here we have a transfer of by Alice to Bob of $30, and that event happened on June 20th, 2019. There might be other, and usually are other events that are important for contracts, notifications, so transmission of information and various other things. But transfers of resources is basically the essence of much of what contracts are about. A contract then extensionally with this semantic model is a set of event sequences. And the set, each element of that one means it's an alternative way of satisfying the contract. So how do we compose, in this case, how do we specify contracts that denote these sets of event sequences? The idea is to do it compositionally. So put contracts together from subcontracts so that those can also be used as subcontracts again. What are the primitives and combinators? We've already mentioned resource transfers. So who is required to give what to whom by what deadline? Then we have basic ones that say, success, which means that this is the completed, done contract. There's nothing else to do. It's succeeded. Or fail, which means it's inherently failed. So there's no way of satisfying it. And there might be other basic primitive specifications of events, which we don't include. So the subcontract combinators are then, given a number of subcontracts, we could stipulate that the composed subcontract is satisfied if any one of them is satisfied, or all of them have to be satisfied, or all of them have to be satisfied, but in a particular order. So all the events have to happen first of one, and then after that, the events of the other one. And we also have the requirement that some events, some subcontracts might have to be repeated. So like a lease, which means that every month payment and rendering actually the room that has been rented must be satisfied. This is captured in the CSL language, the contract specification language. So we have success, failure. Here we have the option, the alternative between two contracts. Here it says that both contracts must be satisfied. Also here, both contracts, but in that order, C1 first and then C2. And here it says that first a transfer has to happen, and then we continue with a residual contract after that, and that residual contract might depend on the actual event that matched this original transfer event specification. And the rest is basically expressing recursion. So this is the basis of Dion Digital CSL. An open access version of that one is available at diondigital.com, and that one's used for applications within bonds, stocks, intermodal mobility, and will soon be used in insurance. How do we relate the specifications to the semantics? We'll do it by choosing a relational semantics, specifying a sequence satisfying a contract specification. In this case, it says the delta is an environment we'll need, but basically, if you look here, the event sequence S satisfies C1 plus C2 if it satisfies either C1 or C2. So this basically expresses that this is the alternative. And the other rules here express in this case that both have to be satisfied in any order or in that particular order here. And as you can see here, the predicate in the event specification here expresses that an actual event must satisfy that predicate here for that to be a successful match. What are some of the general contract properties we might be interested in? Now, not all specifiable sets of event sequences are desirable. So, in particular, a contract that says that you have to give me money and you have to also give me a house is certainly good for me, but it's not a contract, doesn't have any consideration. Or that Alice and Bob enter into a contract that obliges Charlie to pay both of them money is also silly because Charlie didn't sign off on that one, and if he had, it wouldn't have any consideration. So the idea is now to check general properties or properties of general interest. So who's participating in the contract? Who may be obliged in some execution to do something? In which case, we better have their signatures, so they're to participate in that contract. And are all executions fair? So is any given execution such that the exchange of resources is roughly equivalent? It's fair. So this requires an external valuation. Static analysis then will approach as follows. So we want to make sure that we can analyze arbitrary contracts. So the approach is, for a given abstract interpretation, formulate an abstract domain A. So the abstract domain A is an abstraction of, so each one of those elements of A denotes a set of contract executions. Now then, we'll make sure then that this interpretation is sound in the sense that the abstraction we get always denotes a set of executions that contains the actual sets of executions that the concrete semantics has. And from that result A, then we can extract analysis results. So for example, a superset of the participants, or an upper bound on the unfairness of the values exchanged. So if that upper bound is small enough, we might consider that that's a sound and good contract. Still, it's not unfair. So with that in mind, the approach is that given a certain analysis we're interested in, find an A and a concretization function gamma, and abstract interpretations of our combinators, such that they behave nicely. What does that mean for plus, for example? It means that the abstraction of C plus C prime, remember we have an abstraction of C and C prime, will combine the abstractions, the abstract values, and they should satisfy then that the set of executions they denote is better be a superset of the sets of executions of the component contracts. So this is expressed here. As a theorem, then we get that the concrete set of executions is always contained in the concretization of the abstract interpretation. The major challenge in this setting is the formalization and the mechanization of the abstract interpretation for infinite unfolding of recursion, so including iteration. I will not go into this anymore. Please refer to the paper, and in particular to the implementation that is available. So the contributions in general of the paper are multiple semantics of CSL, denotational, relational, and a small step semantics. So think of that one as the interpreter that monitors the execution of a contract, so that it responds one element, one event at a time. It checks whether that's an expected event and can be accepted, and whether the contract then after that still can be satisfied or not. And these are proved equivalent. The static analysis framework is based on abstract interpretation of natural semantics based on Schmidt's method, and we have example analyses. And all that is mechanized, so the semantics, the equivalences of the semantics, the abstract interpretation framework, its soundness with respect to the concrete semantics, and example analyses in Cox. So the source code here contains the details. So let's just briefly discuss how this relates to Ethereum-style contracts or smart contracts. So a smart contract is basically you can think of it as a combined contract, control, and settlement in a general purpose programming language. So by contract here, we mean is like the rule book, the specification of what the parties have to do, and the control is then the action of an automated system that monitors these control, and it furthermore maintains an account of who owns what. So it performs also the settlement of the transfers of resources. In our setting, we're trying to keep these very much separate. So a smart contract, the motto is a smart contract is contract plus control plus settlement. This is analogous to Kowalski's algorithm is equal to logic plus control as a basis for logic programming. What's the point of that is that we can vary actually each part then separately without having to vary the other ones. So we can take the same contract in our CSL language and have it controlled or executed under different platforms, different blockchain systems, or a centralized service system. We can also have various kinds of access control built in, or logging and various notions that will not have to be the same. And the settlement also is separated out from the control, so we can refer and use multiple different settlement systems. So this is motivated by this picture here of a contract-oriented business architecture in real life. So we have, let's say a company A and B, they're interacting through a contract with each other. So each one of them is has private information that they're using or to engage and decide how to satisfy what to do exactly as part of that contract. They might be using, and they will usually require third parties to help them execute their contract. So this might be an exchange or a broker or a notary that helps them, do these things. And in particular, they will usually use a resource manager, in fact, multiple resource managers, namely the ones that maintain actually who owns how much money, who owns which building or house, who owns which car. And this is there to make sure that somebody's engaging in multiple contracts does not overspend, double spend, so doesn't just promise to deliver money to multiple counterparties that they don't own. And we'll just, the IT architecture we have here in mind is exactly a picture of that one. So we have separate contracts, confidential. We have multiple different contract managers that can be chosen by the companies. In principle, per contract, its own contract manager. Think of it as an automated system, and that one can manage multiple resource managers and access both blockchain systems and regular system through APIs, like the banking system, like in Europe now, through the PSD2 directive. And here's another one. So there's, of course, a lot of work on contract specification, analysis, and verification, but I believe actually our work is interesting in the sense that it's fully verified and mechanized for static analysis. So it's not just a single contract that's being analyzed and proved to have certain property, but it's the complete abstract interpretation of the static analysis of contracts, and even a framework for doing this one. So I hope we'll have you